it's a good time. Right. Yeah. Firstly, I would thanks Aditya for accepting our invitation and joining in
Yeah,
for
it's a
the
pleasure.
lecture. It's really nice to have you here. Just to introduce Aditya, he's a assistant professor at the Indian Institute of Science in Bangalore, and he works in the Department of Computational and Data Sciences. I think just like what we were discussing a few minutes ago, like the kind of data sizes that you're dealing with. Probably says that you're in the particular department there, right? And before joining ISC, he was a postdoc at Sandia National Labs in the US. And then before that, he had his PhD in aerospace engineering from Texas A&M and a master's from Georgia Tech and also from JNCASR Bangalore. I'm looking forward to the lecture, and I'm sure it's really interesting. From you kind of given us a tidbits of it, so kind of really interesting to hear about what you have to say. Thank you, Aditya, for joining in. And I mean, if somebody has any questions, I think it's okay to unmute yourself to
Yes.
ask the question. We are more than kind of moderating. We are more in a mode where we are kind of trying to have a discussion and try to understand the topic a little bit better. There's no simple question. You can always ask any question. And I think Aditya would also be very happy to answer it.
Sure.
And we would definitely, after the lecture also, we'll try to have a bigger discussion session. And just to give some idea for the participants who are probably new here. And thank you, Aditya. The stage is all yours.
Yeah. Yeah. Thank you, Ajay, and thank you, Chandan, for extending this invitation. It's a pleasure to speak at this venue. So, yeah, as we were discussing, right, we mainly deal with simulations at really large scale. So, by really large scale, we mean in that we use some of the big supercomputers in the top 10 list of the world. So today I'll be presenting specifically about a method that we have developed recently for solving PDEs at extreme scale. And this method we refer to as a asynchronous computing method. So let me, yeah. Okay. So as Ajay mentioned, so please feel free to stop me if there are any questions. I'll be happy to go over things. So yeah, before I start, I would like to acknowledge Ajay and also my collaborators, Diego Danzis, Thorsten Hofler, Hemant Kola, and Jacqueline Chen. So in addition, there are around 3 or 4 students in my lab who are working on this topic, and hopefully I'll probably get some opportunity in future to present those results in a year's time. So here is the outline of my talk. I'll start with a brief introduction on why we need numerical simulations, how PDEs come into picture, what kind of methods we use for PDEs, and then we'll discuss more about PDE solvers, the parallelism involved there, why do we get parallelism, and so on. And then I'll move on to the asynchronous computing method, where I present the concept of this framework, and then talk about the implementation details. Finally, what performance gains we get out of these simulations. At the end, I'll present the highlights of some of the works that we are doing currently at IISc, and finally end with some conclusions. So yes, so here what you see are pictures of different flows. The first one is from isotropic box simulation that was done on a 4096 cube grid, so which is about 1.6 billion grid points. The second one are the pictures from the Indian Institute of Tropical Meteorology, Pune, where they use the climate code to understand the monsoon in the Indian subcontinent. On the right, you see 2 simulations from scramjet and gas turbine combustors, which we have performed recently. So all of these simulations were done based on some partial differential equations, and this is a typical workflow that we follow. So you have a set of governing equations. These are conservation of mass, momentum, energy, and when you go into the reacting flows, these also include the conservation of species. So these equations are typically discretized into an algebraic form by using any of the standard numerical methods like finite difference, finite volume, or spectral methods. And once we have that, we translate these algebraic equations into a code and we perform simulations. At the end of the simulations, we get data which we analyze to understand a particular phenomenology or a particular challenge that we are observing in the problem that we pose. So this is a typical workflow that we follow. And with these 2 new technologies, HPC and machine learning and AI, So how do these augment, or how do these accelerate the simulation workflow is what I'm going to present next. So with HPC, we are now able to perform simulations at a really large number of grid points. So currently the state-of-the-art simulations are being performed on billions of grid points. And with these simulations, we generate large volumes of data. Currently, we are generating data of the order of terabytes, and in future, as we move towards the next generation exascale computing, the data will be of the size petabytes. So that means we need intelligent workflow to do data management, right? And typically what we want to do is we want to detect patterns, anomalies, or create a subgrid models like reduced order models to using machine learning to have an efficient data management as well as analysis. Where does this data reside? So you cannot have all the terabytes or petabytes of data on a single machine, right? So the data now will be on a cluster or a supercomputer in a distributed fashion. That means the machine learning and AI should again interact with HPC to perform distributed data analysis. So this is a typical workflow that we would expect as we move towards the next generation supercomputer. So here I want to bring in a brief picture of turbulent flow simulations. What we perform are the direct numerical simulations where we resolve all the scales that are dynamically relevant, both in space as well as time. So if you consider the canonical or the standard turbulence theory, so you have the large scales L and then the smallest dynamically relevant scales, the Kolmogorov scales eta. So if you use the classical scaling theory by Kolmogorov, the scale separation between the two, which is the ratio of L over eta, scales as Reynolds number power 3/4. So where this Reynolds number is based on the integral length scale. And next, this Reynolds number is typically high in practical applications. So you can expect something of the order of 10,000 to 20,000. Currently, even if you take the simplest isotropic turbulence, we are able to reach only up to around 2,000 Reynolds number. This is in terms of Taylor microscale. So now how does the computational effort scale with the Reynolds number? The relation is given here. If C is the computational effort, your Reynolds number, if RE is the Reynolds number, the computational effort scales as the third power. That means you double the Reynolds number, your computational effort goes by 8 times. So this means that as we go to higher and higher Reynolds number, we need to resort to parallel computers or parallel computing methods to obtain the numerical solution of the flow equations. So here I talk about what has been happening over decades, right? So we take this simplest form of turbulence simulation, which is the isotropic turbulence simulation. Here we perform the DNS using pseudospectral method and RK for time stepping. A typical realization is the picture that you see here. This has multiple scales. So for example, you see this bright patch, and within this bright patch, there are smaller and smaller structures. So these demand high grid resolution, which in turn demands a massively parallel computations. So here on the right, I show a graph on how computers have evolved, or the supercomputers have evolved over several decades. So these are represented by the blue dots. And currently we are at a scale where we have Summit, or the Japanese supercomputer, which is around half an exaflop, right? And let's see, with the increase in the amount of supercomputer power, how did turbulence simulations, specifically the isotropic turbulence simulations, evolve? So the first simulation was done by Pope and his student in 1970s. So there they have used the pseudospectral method and used Runge-Kutta time stepping. As we evolve from there to the current state of the art, what has happened is the numerical method has remained the same, right? However, what has changed over the years as the supercomputers evolved is the way the parallelism is done. So that means so initially they were looking at vectorization, then they came to these OpenMP concepts. Then as you move across different nodes, you have these PVM or MPI, and now we have accelerators like GPUs, and also looking at the more advanced ones like FPGAs. So that means the numerical method has been the same. However, the major developments over the years to achieve higher Reynolds numbers has been to change the way parallelism is done. Okay, so I take one more example here. This is from the S3D code from Sandia, which I have worked on extensively. Here we again show how the simulations have evolved over several decades. So in 1995, if you take, we were able to do only 2D simulations, and that too with a single step chemistry or a simple model for chemistry. As things evolved, we are getting into detailed chemistry, and also now the current simulation, we are able to go to complex geometries which are relevant to practical simulations, right? So here, this was something like a single step. Now we are able to do detailed chemistry with around 116 species. So we solve around 120 partial differential equations at each grid point, and we are solving them on billions of grid points and integrating them in time for millions of time steps. So that is the kind of computing that we are looking at as we move towards the next generation. So now let me talk briefly about PDE solvers and how to introduce parallel programming concepts here. So for the reacting flows, these are the set of equations that we solve for. We have the conservation of mass, momentum, energy, and species. And these equations can be solved using any of the methods. So here I'll focus on finite difference methods, but you could also use finite volume, finite element, pseudo-spectral, and spectral element methods. So in most of these methods, the broad way the solvers are designed remains nearly the same. So initially you perform an approximation for the function or the equations. You discretize the domain, you specify the initial and boundary conditions, and then you have an algorithm to evolve the solution in time if you are solving the time-dependent PDEs. So let's look at that with a much more simplistic equation here. We consider a simple 1D heat equation. You have the time derivative on the left and the first one-dimensional spatial derivative on the right. So this equation can be solved on a rod of length L. So this can be typically thought of as a simple heat conduction problem where you specify some heating element at L or 0 and then try to understand the temperature distribution, right? So to solve this numerically, we divide this whole domain into several grid points. So these are the grid points, and any generic grid point can be named as I here. So now the U, the function U, is defined at each grid point and at each time level. So now we have the next step is to approximate these derivatives, right? So we apply a typical finite difference. For the time derivative, we use a first order forward difference. So here you have ui at n plus 1 minus ui at n. So where ui n is a known solution and the unknown is in the blue color, which is ui at the next time level, which is n plus 1. This scheme is first order accurate in time. And also to approximate the right hand side derivative, which is a second order spatial derivative, we use a second order central difference. So this is a typical formula, and this is second order accurate. And this approximation can be done in two ways, where you can define the spatial derivative either at a time level n, where all the function values or all the u values are known, or you can define these approximations at time level n plus 1, where all the three are unknown. So in the first case, this is called an explicit formulation, where you end up with a matrix vector multiplication to obtain the final solution. Or in the second case, you will end up with a linear system like Ax equal to b, and you have to use either direct or iterative solvers to come up with the evolved solution. So how do we implement this? So this is if you consider the explicit schemes in this finite difference equation, this is the only unknown. You take all the known ones, the black terms on the right hand side, and you will finally end up with a vector form which is given like this. So you solve this equation in the entire domain. I've given a simple pseudo code to perform these computations. So you have a time loop which starts from 0th time to goes until the last time step nt. And you also iterate over all the grid points. So you start from 0 and the next. And this is a kind of update equation that we would obtain by rearranging the terms in the above equation. So at this point, I will pause for a minute and I'll be happy to take any questions. Any questions? I mean, I know that this is very basic material, but I was assuming that there would be some students. So in that context, I thought that it might be useful to have a brief pause here. Any questions?
I think there's a question on chat.
Yes.
How the equation will change in the case of multiphysics problem? I think slide 10 or something.
Okay. So in the multiphysics space, I'm not an expert on that, but you will have equations for the, let's say you consider liquid gas phase, you have to track the interface, right? And okay, so let's say particle immersed. So if you consider something like immersed boundary methods, right? So you will have the solid region and then the fluid region, and you will solve. You have to adjust the boundary conditions based on interpolation functions and so on. Again, I'm not an expert on that, but I think you could use these kind of methods there also, and they are extensively being used in the community. Any other questions?
Aditya, just a question. I mean, I was curious about
Yes.
the pictures you had on the first couple of slides, where they had done these
Sure.
monsoon simulations over the entire Indian subcontinent. So are these?
No, that was not me, but yes, go
I see.
ahead. I did not do the simulation. I just picked it up from IITM website,
Okay, I see. Okay.
just as an illustration.
Okay. Then it's okay. Okay. I was just curious as to like, was it just like a wind simulation, or did they do some wind water simulations? I was just curious about that.
I don't know. I just put it for aesthetics.
Okay, no problem. No problem. Thank you.
Yeah. Okay. Yeah. So now with these kind of numerical methods, something that is also important is to look at their numerical properties, which would dictate whether we would get an accurate solution or not. So typically we look at three of the properties, which are the stability, consistency, and accuracy. And these depend on several parameters, which are listed below. So they depend on how finely you are resolving the solution, like the grid resolution or the number of grid points. It also depends on the nature of the partial differential equation that you are solving, whether you are solving parabolic, hyperbolic, or elliptic equations. And then also depends on the parameters of the equation, which can be which are like the Reynolds number, Schmidt number, or the numerical parameters like the CFL condition. Okay, so now let's briefly discuss the parallel implementation of this heat equation. So let's consider computation of the function value at point I at n+1 time level. So if you are doing it on a serial computer or on a single serial code, all these function values are available in that particular processor's memory, right? So which means that you can access whatever value that you want from the stencil to perform these computations. Okay, so when you do the same thing in parallel, here what I consider is a data parallel or domain decomposition method. We divide the domain, which is this 1D domain, into let's say two processors. So processing element 0 and processing element 1. So now what I want to do is I want to compute this stencil operation or update this finite difference equation at this point I. Okay, this point I needs a function value from I+1 and I-1, which comes from the requirement of the spatial derivative. Okay, so but I-1 is being computed in my neighboring processor. So what we do to access that value is we create a ghost or a buffer point and communicate that value that is being computed in the neighboring processor over the network, right? So we perform a communication, which is usually done in two steps. So you initiate the communication where each processor will get a message or send a message to each other that I want to send a value, or the other processor will say that I want to get a value from you. And so that is the initiation of communication. And then finally, to ensure that the communication has finished or the value, the message packet has reached the destination processor, we enforce what is called the synchronization. Okay, so this synchronization will ensure that the function value u at this point I-1 is at the nth time level. Okay, and hence you can go ahead and compute this finite difference equation at this point I. For all of the points that are colored in black, all the stencil points that are needed for its update are available within the processor's boundary. Okay, so this is the point that I want to make. So now what happens? How do we implement this communication? So I'll give you a simple example based on MPI, a programming model. So here what they do is the source processor will post MPI send, and then the destination processor which has to receive the value will post an MPI receive. You can also do it with a single command called MPI send and receive when both of them are exchanging the values. So these are called blocking communications, where all the processors will remain idle until the values have reached the destination processor. So you send a value and you wait for the without doing anything else. You just wait for that value being received into your memory. and then only you move forward with the further computations. Okay, so these are called blocking communications. The second set of example consists of non-blocking communications, where the commands are MPI ISend and MPI IReceive. So what they do is they initiate the communication, and then they let the processors go ahead and do some other tasks that are further in the queue, and then you post a wait whenever you need these values, and then perform a synchronization call and communicate and perform computations. So these are referred to as non-blocking communications, and these will help us achieve what is called a computation communication overlap. Okay, I'll just reiterate this. So, when we do parallel efficiency, or when we talk about parallel efficiency, we don't want CPUs to remain idle. So what we can do is we can use these non-blocking communications, which will start the communications, and then you go ahead and compute something else which is independent of communication, and come back and do the computations that depend on communication once the message is received. So this means that overall you are able to keep the processor busy at all the time, which is what the processor should do, and you will maintain an efficient code. Okay, so this is what happens. So again, I just do the same thing here. So in the non-blocking communication case, you have MPI ISend and IReceive, and once you have done the overlapping computations, you post an MPI wait, which is a synchronization call, and then go ahead and compute the necessary stencil operations at the processor boundaries and move to the next time step. Again, I'll come back to all of these things in the asynchronous context in after a few slides. Okay. So now let's talk about what is the efficiency, or how do we measure the scalability of codes in parallel computing. Let's say I want to perform a simulation in this box. I perform it on a single processor on a serial using a serial code. Let's say T is the amount of time that it takes to compute the solution. Okay. So now what we do in parallel computing is we divide this domain into, let's say, two halves. So now you give the first half to the first processor, the second half to the second processor. So now to perform computations, we also need to perform communications, which are represented by these arrows. So now in this case, ideally, the code because we are using two processors simultaneously, the time to compute should reduce by half, so which is T/2. However, because we have this additional communication, we also add what are called the communication overheads, which is represented by this C2 value here. Further, if we divide the number of subdomains into 4 processing elements, you have now 4 subdomains. The computing time reduces to T/4. However, you see that there is a significant increase in communications, or the number of arrows, and the associated communication time is C4. Okay. So when you do parallel computations, ideally what we are interested is in reducing the computing time. However, what you see is there is a slight increase in the amount of communication time as you increase the number of processors. So now we define what is called an ideal scaling. So in general, let's say that we have P number of processing elements, and C is the total computing effort. Then the time taken for the computations to be performed with C as the effort and P as the number of processors should scale as C/P. Okay, right? So this is the ideal scaling law, where it shows that the computing time is inversely proportional to the number of processing elements that you have used. So I will now show you on the right a picture of what is called a strong scaling graph, where we increase the number of processors to perform a simulation, in this particular case of isotropic turbulence with 1024 cube grid on back then the Kraken supercomputer at Oak Ridge. And we measure the time taken to perform one time step of calculation. Okay, so we start from something like around 1024 or 2000 processors. We go all the way until 16,000 processors. So these red ones are the observations that we get from our simulations. The dashed line is the ideal scaling line that is obtained using this scalability relation, linear scalability relation. So what we observe here is, as we increase the number of processors, the stars deviate or move away from this dashed line. Okay, which means they are incurring more amount of time to perform one time step when compared to the smaller number of processors. Okay, again, which means that the communication overheads are increasing with increase in the amount of number of processors. So this is
Aditya,
called.
can I interrupt you?
Yes.
I'm sorry. So
Yes,
I
please.
was curious, how do you estimate this computational effort?
Okay, you can, I mean, there are two ways. You can do it here heuristically, right? Where you know how many number of equations are there, how many number of, what is the typical number of calculations that would be incurred in each equation evolution, and so on. So with that you can get something. But the other way to do this is to have a specific timers with the that are exclusive to the computational blocks of the code, and accumulate those over several time steps and do an averaging.
I see.
Does that
Okay.
answer your question?
Yes, sure. Yeah.
Yeah. Okay. So usually that time we would expect to go over the number of processors as we increase the number of processors. So that would follow this ideal scaling line. But what we observe in practical observations is that you deviate from this ideal scaling line, and this is mainly because you have this increase in the amount of communication. And as you go to the large number of processors, there are more number of communications, and then the network length also increases. So the latency costs and everything increase, and resulting in what is called inefficient or poor scalability of codes. Okay, so now let me move on to the next slide. This slide I want to show what are the issues that we are going to face as we move to the next generation supercomputers. So currently we are in a petascale era where we are able to now achieve 500 petaflops, so 500 double precision floating point operations per second on on one of the top supercomputers in the world. The next generation will have double power of that, which is about 10 to the power of 18 calculations per second. Okay, so that is exascale. So, and these exascale computers would consist of CPUs, GPUs, and also FPGAs. And all of these will be connected using a complex interconnect. I show you just a couple of examples here, right? You see so many lines connecting each other. And if you actually see the amount of cabling that is needed to connect all of these, that would run into like almost several kilometers, right? And what would this add to? This will add to large number of communications that are happening between processors. So think about the traffic in Bangalore, how bad it is, right? So that is the kind of situation we will get into. And this will increase the communication time and affect the scalability of code. So the whole purpose of running this code is to do computations. But if you are spending most of the time in communication and not on computation, then it is an inefficient code. So that is what we mean by affecting the scalability or the performance. And then when you have about million processors, right, there is always a possibility that one of the processor would fail, or one of the processor will not perform to the peak of its rated performance, right? So this is typically referred to as performance variance issues, which might result from either system noise, or you probably do not cool one of them properly. So that means if one of the processor is running slow, it is going to slow down the whole machine, right? Because of the data synchronization and data movement, which I'll explain shortly. And the next thing is the synchronization that is enforced at multiple levels. So as you have seen in the earlier example of the simple 1D heat equation, so we cannot proceed with the finite difference update unless we receive the value from the neighboring processor, right? That means we have to wait if that is not received. So that is what we call as synchronization. And this can be enforced at a communication level, at a mathematics level, and even at a hardware level. So I will discuss about the mathematical level in the next few slides. And then I also just briefly mentioned earlier, we talk about system faults. So you have million processing elements. One of the memory might fail, one of the communication module might fail, or one of the processor itself might fail. So in this case, the whole simulation cannot go waste, right? So you want to come up with some kind of fault tolerance mechanisms to actually address some of these key challenges. So what are these? So in this slide I have mentioned the issues, and now I'll talk about some of the solutions that are being worked on as we move towards exascale. So the parameters for the solution are these. So we want to minimize the data movement. We want to reduce the amount of synchronization so that we can do more amount of computing. And we also want to express data locality and independence. So that means you want to do as many computations as possible without any major communication requirements or data movement requirements, because So what people typically say is flops are cheap, but data movement is expensive as we move towards exascale. So if you consider that mantra, right, so you want to do optimize all of these parameters. So in terms of research at a software level, people are coming with asynchronous runtime systems, which allow you to perform asynchronous communications, and you also have asynchronous programming models. In terms of mathematical level, what we are interested in is developing asynchronous numerical methods. That means numerical methods that actually relax the data dependency in the stencil operations or in the finite difference equations. And if we combine all of these things, what we can achieve is a co-design fashion. In a co-design fashion is the asynchronous computing method. Okay, so now I will briefly describe what is this asynchronous computing method, how we start from the mathematical level and go all the way to asynchronous programming models and achieve a scalable code. Okay, so now again I'll come back briefly to the context, to the simple heat equation example. So here you have the finite difference equation. As I mentioned earlier, in the serial processor, all the values are there in that particular processor's memory, and the computations are readily performed. In the second case, where you decompose the domain into two halves and distribute them to two different processors, now you have to, in order to compute the finite difference equation at this point I, you need the value at I minus 1 and I plus 1. I plus 1 is available with the processor, but I minus 1 is not available with the processor. So what you do is you create this buffer point and communicate the I minus 1th value from the neighboring processor over the network. This is done in two steps. First, you impose communication initiation, and then you enforce synchronization to ensure that the function value and this buffer point or in this piece of memory is at a time level n. Okay, so now let me propose what is this asynchronous concept. In the asynchronous concept, what we do is we communicate. That means we initiate the communication between the two different processors. However, we do not enforce any synchronization. That means the processors will not wait for the value to reach this destination. If the network communication is really fast, then the value goes and you have the latest time level available. If it is the communication is slow, you might actually end up taking an older value and communicate the stencil operation. So what does this do to our finite difference equation, right? So this is what we have here. So now if you consider this stencil operation at this point I, the unknown that you want to compute is the blue color one, the function u at n plus 1th time level. It uses all the older values. In this particular case, if the communication is not finished, you will have a value which is not n. So we call that as n tilde. Okay, and this n tilde, depending on how fast the communication is, can be either from the time level n, n minus 1, n minus 2, and so on. If you have a really lousy network, you might end up with really older values. So that means if you take an older value and start computing the solution, will you still be able to get an accurate solution? That is the question, right? So, and hence we have the question marks here. Okay, so we do not know if you take an older value and compute whether the solution is going to be accurate, consistent, stable, and so on. Okay, so just to summarize this asynchronous computing method, all the points that are in the black color for which the values are available in that particular processor memory are done in the old fashion. However, when you come to the processing element boundaries, where the data now, the computations now depend on the data from the neighboring processor, we perform the computations asynchronously. That means the time level here need not be at nth level, but it can be any of these time levels. And as the arrival of messages between different processors in a network is random, this n tilde actually takes is a random variable, and it can take any of these values. Okay, at one time step it can take an nth value, in the second time step it can take n minus 1, and some other time step it can take n minus 3 value, and so on. Okay, so now this equation is not deterministic anymore, and this has the stochastic nature that comes up from the time level of the function that we have in the stencil operation. So I will pause here for a minute, and I'll be happy to take any questions on the concept of asynchronous computing.
Yes, I have a question here. So what is the
Yes.
advantage of bringing in this stochasticity? Can, if we, let's say, stick to a particular previous time step value that we already know, so what is
Yes.
the difference in concepts actually?
Okay. See, that's a very good question. So you have actually brought up a topic of communication avoiding algorithm versus a synchronization relaxing algorithm. Okay. So let's say that if you always impose a constant delay, right? A determined constant delay, you can avoid communications for few time steps. Okay. But
Yes.
it is also possible that you can communicate at every time step, but not wait for that communication to finish. Let it be let's complete those communications at their own pace. In some cases we might actually do it in a faster way if the processors are very local in nature, the latencies are smaller. But if they are really far apart, or if there is a network congestion, you will get a much delayed value. Okay, so now you will leave it to the system and then let it compute with whatever value it has. So in this case, what we will find, or what I'll show in the next few slides, is that the greater the delay, the greater is the amount of error that you incur. So now if you have a probabilistic system, right, you might actually get more synchronous values in some cases and less synchronous values in the other cases. In the earlier case, it is all uniform, predetermined
Yes,
amount
yes.
of delay. Yeah. So yes, that's a very good question. In fact, we are working on it for GPUs currently, and one of my students, Vinod, will be writing up a manuscript on that shortly.
Okay, sure.
Okay,
Thank
so
you.
I'll come back to that again in the implementation part later. So I think we have some measurements on that. Okay, so now the question here is, so we do these computations, but how accurate do you even get a stable solution? So that is the question that we want to ask. So we want to analyze the numerical properties of such a method. So now earlier we have seen that the numerical properties depend on the grid size and all the physical parameters, right? But when you do things asynchronously, where you have the stochastic nature and the amount of delay at each grid point, the numerical properties will also depend on the simulation parameters, like what is the stencil size. So whatever I've shown you is a 3-point stencil, which would give you a second order accurate solution. But as you go to higher order methods, like for example, the combustion simulation was performed using 8th order schemes, right? And, that uses around, I think, 9-point stencil. So now the asynchrony will affect all of those stencil points. So we have S as one of the parameters. With the increase in the number of processing elements, more the number of asynchronous computations that are performed. So this also becomes one of the parameters. And you cannot have an infinite delay between two different processes, right? So you still want to propagate the solution. Maybe it is at a slower speed, but you still want to propagate the solution. So you cannot have an arbitrarily infinite delay. So we restrict the amount of delay between two different processing elements in terms of time levels to L. And now with the random nature of communications, right, the different time level values take different probabilities. So those are pk's. So if the k represents the amount of delay. So for example, I define here n tilde is equal to n minus k tilde. If k is 0, the value is synchronous. So if k is 0, n tilde is equal to n, and the values are synchronous. That means these are the traditional way of computing things. But as k takes a non-zero value, these are asynchronous. These are not at the nth time level, right? These are at n minus 1, n minus 2, or even sometimes from future n plus 1, n plus 2, right? So what is the probability of occurrence of each of these time levels? And this in turn depends on all of the parameters on which the code has been developed. The hardware, the software, the compiler, the kind of MPI implementation you have used, and all of these. Okay, so let me take a simple example. Let's say I fix the amount of delay that I can bear to two time levels. That means k can take the synchronous value 0 or one time level delayed value, which is 1, k delay equals 1. If in my simulation, I get 0.6 times a synchronous value at these buffer points, that means 0.6 times your communication got finished in time, and 0.4 times there was a delay, right? So you get this probability distribution. Okay, so before we go ahead and show you the results on numerical properties, I want to quickly do a simple numerical experiment using a simple linear advection diffusion equation. We use second order accurate schemes for space and first order Euler in time. We use a combination of sine waves as our initial condition. This equation for periodic boundary conditions as a simple analytical solution that is given here. We use this analytical solution to compute the error in the simulation. Okay, And to perform the simulation, we use some kind of simulated delays where the delays match some kind of a distribution that we observe in one of the supercomputers. And we use a time step that is based on the diffusive CFL. Okay, so now if you consider the asynchronous computations at these points I minus 1, that means at these two stencil points, we would get delayed values. And this is a finite difference equation. So now let me show you the results from the numerical experiment. Here I take a simple sine wave of wave number 2. That means in the 2 pi domain that we have, you see two sine waves. As we move, as we evolve the solution from the initial condition, because of the advection effect, the wave moves to the right with a constant speed, because this is a linear advection equation. And because of the diffusion process, the amplitude of the wave decreases as we move in time. Right, and on the right, what I do is we compare this solution with the analytical solution. So obviously, as you evolve the solution in time, the error increases, and it also takes a shape that is either a sine or a cosine because of the linear nature of the problem. So now let's do the same thing. So this has been done in a synchronous fashion, or the traditional way of computing things in all the PDE solvers, where you wait for the communication to finish and then go ahead and perform the computations. Now, in the next step, what I do is I perform asynchronous simulations. So that means we don't wait for the communication to finish. We take the values to be whatever they are in the buffer points and then go ahead and compute. These can be synchronous values or the delayed values. So what you see on the left graph is that the black line matches the dashed red line. So the synchronous and asynchronous solutions look nearly the same. However, this might be a little deceptive. So we move to the right graph where we look at the errors. Now, if you see the errors in the black case, these are on order of magnitude more than the red ones. Okay, and these sharp peaks, they actually occur at 4 different locations that correspond to these dash dotted lines. So here in this simulation, we have used 4 processors, and at these 4 processors, we get delayed values at these boundaries, which are depicted by these dash dotted lines, and this is where the asynchronous computations are performed, which means that the asynchronous computations result in these huge errors. And these errors, as you see in time, would propagate into the interior of your domain and corrupt the solution there as well. So now the question we want to ask is, do these errors amplify in time? That means is the numerical scheme unstable, or they diminish in time, which means the scheme is stable. So to analyze this, we plot the accuracy graph with increasing grid resolution. So now what we do is we compute the overall error in the system as an average error, let's say. And for the synchronous case, which is this red line, because we have used a second order accurate scheme, as we increase the number of grid points, we see that the error drops with a slope of -2. Okay, second order scheme scales as a delta x square, which means it scales as delta n power -2, and hence the slope -2. The black line is just a reference line which says that the slope is -2. Now we introduce some amount of asynchrony. So we move from the red color to green, blue, and magenta. As you move from green to magenta, we increase the amount of asynchrony. That means more and more delayed values are being incurred at these buffer points. So what we see is that as we increase the number of grid points, the error is decreasing. That means it is good. So that means the scheme is stable. However, the rate at which the error is increasing has dropped from -2 to -1. Okay, that means the order of accuracy has gone down from a second order accurate solution to a first order accurate solution. With the increase in the amount of asynchrony, what you observe is the slope still remains to be -1, but what you see is an increase in the absolute magnitude of the error. Okay, so the takeaways here are the numerical scheme is stable. That means as you increase the number of grid points, the solution error is decreasing. However, there is a drop in accuracy of the solution. It is becoming a first order accurate solution instead of a second order accurate solution. And also with the amount of with an increase in asynchrony, we are also incurring large amounts of error. So can we explain this behavior that we have seen from the numerical experiments? For this, we have developed a new framework which takes into account the stochastic nature of the numerical method, right? And we try to analyze the stability, consistency, and accuracy. So in terms of stability, what we have observed is that if the basic scheme in the synchronous case remains stable, it will continue to remain stable even in the asynchronous case. And we can also show the consistency of these methods, and these are presented in the references here. But what I will talk about in the next few slides is about the accuracy, which strongly gets affected, as you have seen in the previous graph. And we want to understand can we go to higher order? What is the spectral accuracy of these schemes? How will the error propagate in time and space? So these are some things that we want to understand. So now for that, we use the simple Taylor series expansion and obtain what is called the truncation error. Truncation error is the difference between the actual PDE minus the finite difference equation using the Taylor series. And this is the truncation error that we obtain at a grid point I and a time level n. So the first term here is the term that contains delta t and the time derivatives of u. This is the leading order term that comes from the truncation error of the Euler scheme. The second term is the leading order term that we obtain from the approximation of the spatial derivative. The third term represents the higher order terms in the Taylor series expansion. So this is done for a synchronous case where your n tilde is equal to n. Now let's say that we delay the whole simulation we delay the computation by one time level. That means your n tilde is equal to n minus 1. Okay, so now what you see is, in addition to these two terms being the leading order terms, you introduce whole of these red color terms that are now as a consequence of the asynchrony in the simulation. And if you see the order of these terms, these are of the order delta t divided by delta x square. And if you use the diffusive CFL condition, you will see that this term is zeroth order accurate. And these red terms are specifically responsible for the degradation in the order of accuracy and increase in the error in the solution as we do asynchronous computations. Okay, so now let's say that I take an arbitrary amount of delay. So instead of n minus 1, I say that the delay is k time levels. So n tilde takes a value of n minus k tilde. And here you would see that the factor k does not affect the exponents of either delta t or delta x, but they appear as a prefactor. That means this is consistent with what we have observed in the numerical experiments, where we saw that with increase in the amount of delay, we don't change the order of accuracy of the scheme. That means the exponents of delta t and delta x are not getting affected. But what we are changing is the magnitude of the error, where k is appearing as a prefactor for the error terms. Okay, so with this understanding, we went ahead and computed the overall error in the domain. The overall error in the domain can be taken as an average of all the errors at each of the points. This can be further split into the blue and red terms, where the blue ones are computed at the interior points where you do not experience any asynchrony. And then you compute the error at the red terms where you experience stochastic time level delays. And hence we have to do some ensemble averages and so on to get the relation. So we substitute the expressions that were there in the previous slide into this averaging process, and we will finally end up with a scaling expression for the error, which shows that the error scales linearly with the mean delay that is experienced over the entire simulation, and also scales linearly with the number of processors that were used in the simulation. And then you will see that the error now goes as 1 over n, or goes as scales linearly with delta x. So now we have to interpret the error in two different fashions. Typically in HPC, you scale a simulation in two ways. The first one is called strong scaling, where you take a particular problem size and increase the number of processors. So as you increase the number of processors, your time to solution starts reducing. In the second case, what is called the weak scaling, you take the computational effort per processor to be fixed. And when you increase the number of processors, you try to solve a bigger and bigger problem. So ideally, the computing time should remain the same. But as you increase the number of processors, you are now able to solve bigger and bigger size problems. In the first case, we would obtain from this relation that the error is first order accurate. In the second case, you would obtain that the error is zeroth order accurate. So this theoretical framework has been validated using several numerical experiments, which I'll show you in the next few slides. And this is presented in the reference given below. So what we have seen here is the error scales linearly with number of processors. So we do that here, and we see that as we increase the number of processors and as we increase the amount of grid resolution, the solution goes from a second order accurate to a first order accurate scheme. And with the amount of with increasing the number of processors, the error is increasing. To understand the scaling, we plot the error versus the number of processors in the inset graph, and you see that with the increasing number of processors, you observe a linear scaling in the error. Okay, and when you go to the weak scaling, where we predict that the error should remain a constant, you see that the error goes to a constant value as you increase the number of grid points asymptotically. Okay, and we also verify the scaling law in the inset graph. I'll not get into the details here, but if you are interested, I'll be happy to go over these during the discussion. So now that we have used until now a second order accurate scheme, which has an accuracy of first order when done asynchronously, what will happen to a fourth order accurate scheme? Will the accuracy go down to third order, second order, or will it like the second order schemes go to the first order? So that is what we do here. In the fourth order case, in the synchronous one, which is the red line, the error goes with a slope of -4. When you do the same thing asynchronously, the green, blue, and magenta lines, the error drops to first order. You see that there is several orders of magnitude increase in the error when you do these things asynchronously. So now the question we want to ask is, can we deal with these low order accurate schemes and perform something like a DNS? Obviously, the answer is no. When you incur these huge errors with all these spurious oscillations, you will not be able to perform accurate simulation. So that means, can we actually derive new schemes that can actually bring back all of these lines to a slope of fourth order? So for that, we have derived what are called the asynchrony-tolerant schemes, which actually use a stencil that is much bigger in size only for the processing element boundary points. So for example, if I want to compute a fourth order accurate solution, it uses a fifth 5-point stencil. Okay, so that is a synchronous case. When you do the same thing asynchronously, that means there are delays in the values on the right half of the stencil. It will result in poor accuracy, as you have seen in the previous graph. Now, what we want to do is we want to increase the stencil size and remove the terms in the truncation error that are responsible for this degradation in accuracy. So you can expand the stencil in two different ways. The first one is you can add one more stencil point in space, which will result in a 7-point stencil. In terms of HPC, this will result in larger message sizes. Okay. In the second case, what we want to do is we want to expand the stencil in time, where the message size would remain the same. However, what you would observe is an increase in the memory requirement per processor. Okay. So this is what you would observe. So this has actually consequence when you on how you want to design a stencil for a really big simulation. If your supercomputer is memory bound, you want to go with the spatial stencil. If your supercomputer is latency bound, you want to go with the temporal stencil. That means when you choose numerics for next generation machines, you want to choose them not just based on the nature of the equations or physics, but also on the kind of supercomputer that you are running the simulation on. So all of these things come into a complex workflow for next generation simulations. So we derived 80 schemes. I'll not go into the details of that. I'll just show you what a scheme looks like. It looks like this here. It uses a 5-point stencil in space and uses a 4-point stencil in time. And we have derived an analytical expression that would capture the error theoretically, right? And now if you plot the error graph here, you see that all of these lines are now coming up with a slope of -4. And all of these lines incur nearly the same error as we increase the number of grid points, right? So this was done using a simple linear advection diffusion equation, right? And one of the students, Emmet, who has worked with me at Sandia, has also demonstrated this for a reacting flow simulation that was done in 1D. That means we are able to do this for even complex equations. And we also plot on the right side the energy spectra. The red color graph is the one obtained from the synchronous case. The black one is from the asynchronous case. And you will hardly notice any difference between the two. That means we are capturing accurate solutions that are accurate in space as well as in the wave number space. Okay. So at this point, I would like to pause and happy to take any brief questions on the theory part.
I don't have any question on the theory part, but I was just wondering, like, what is your experience? Let's say we have a open source code with us and we
Okay.
want to like simulate a very intensive DNS simulation for understanding different scales of the vortex dynamics, let's say. And if we
Okay.
find that it is weakly scaled,
Okay.
okay, as you explained, so
Mhm.
can we live with this, that, or like what would be the easiest way to improve it?
Yeah, so the first easiest way to see the typical life cycle of optimizing codes for big supercomputers. First, what you want to do is profiling of the code and see if there are any significant communication overheads, right? If there are communication overheads, first thing is you want to use, if your code doesn't use a non-blocking communication, first you want to use a non-blocking communication and do a computation communication overlap. What you will observe is that typically this would improve the scaling when you are on a supercomputer with around 10,000 to 100,000 processors or 1 lakh processors. If you want to go beyond that, communication becomes a real bottleneck, as we observe in many of our simulations. And then we want to incorporate this asynchrony at a mathematical level. So what we want to do is the stencil operations that are performed at processor boundaries have to be changed to the new schemes, and then you will be able to perform things asynchronously. And we have implemented that. So in the next subsection, I will show you the implementation results and how well we scale in terms of increase in number of processors.
Okay, I have another naive question. So basically, you told
Yes,
that which the supercomputers, those are not memory bound, like those are latency
yes,
based. So I don't know
yes.
exactly what that means technically, but
Ah,
you asked actually that we should go for a temporal stencil. I mean, temporally we should select the scheme instead of numerical. Sorry, a spatial stencil. So can you please
right.
elaborate on that? Yeah.
Sure, sure. See, traditionally, when you look at finite differences or finite volume, to compute the derivatives, spatial derivatives, we usually use points only in space, right? You pick the neighboring grid points. If those are not enough, you expand to further neighbors and so on, right? So usually the stencil is being expanded only in space. So if you increase the number of points in space, you will incur larger message sizes, okay? So now larger message sizes means that a communication. So first thing is I want to define what is latency. Latency is the amount of time for a single packet of message to reach from one processor to another. Okay. So for example, you can think of like you have a overhead tank in your area, and then how much time does a fluid parcel take from the overhead tank to reach your home? So that is the latency, right? The bandwidth is can be thought of like if I want to pump, right? So many liters of water per second, right? So that is like a bandwidth problem. So
Okay.
now, as you increase the message sizes, what will happen is your communication now becomes bandwidth bound. That means you cannot send the entire message in a single packet. You have to send several packets for your entire data to reach from the source processor to the destination processor. In the latency bound case, you just send one packet, but that one packet messaging packet is enough to send your entire data that is required for the computation in the neighboring processor.
I see.
Okay,
Okay. Thank you.
so
Yeah.
yeah, so now so typically when we design these stencils for finite differences in space, right, we usually use spatial points, but what in this paper we show is that we can also use temporal grid points. That means grid point the function values that are at the same spatial location but at a different time levels to compute the space derivative, not the time derivative. Time derivative, of course, we use the stencil or the function values in different times that we do anyway. But even to compute the spatial derivatives, we can use function values at older times. So that is what we are exploiting here. So that is what I mean by the stencil in time.
Okay. Thank you.
Okay. Yeah, I can probably bring up a different figure and show you after towards the end of the talk. So recently, one of the intern, Komal from Texas A&M, has implemented this for more complex reacting flows, including premixed, non-premixed, and as well as autoigniting mixtures and so on. And we also developed asynchrony-tolerant Vino schemes, which are required to capture shocks as well as detonations. So that work has been completed recently and submitted to JCP. Okay, so now let's move on to the implementation part. So now if you consider the asynchrony-tolerant schemes, a typical scheme looks like what is given in this expression here. It might look very uh, uh, what do you call complicated, but what you see is that you have stencil points in space going from I plus 3, I plus 2, I plus 1, I minus 1, I minus 2, and I minus 3. And you have time levels going from n minus k tilde, and n minus k minus 1 tilde. So n minus k minus 1. So there are 3 time levels that are used here. The value of k remains arbitrary because we are considering stochasticity in the time level that is available in our buffer. And what you also observe here is that in the earlier case, the coefficients are all some integers or some fractions. But here you would see that now the coefficients are also a function of the amount of delay, right? So now to implement an algorithm for asynchronous computing which use asynchrony tolerant schemes, these are the necessary requirements. You do communication in a non-blocking fashion, but you synchronize only when your delay between two processors is greater than the allowable delay between in the problem that is dictated by the physics, that is dictated by the time scales associated with the problem. The second thing is you want to store the data from multiple time levels, because if you see at point u at I minus 1, we have values of the function at n minus k and n minus k minus 1. The next thing is we also want to have the knowledge of k, which is the amount of delay, because that comes as one of the coefficients in the stencil operator. And then the last point that I want to emphasize is atomicity. So this is something new for all mechanical or non-CS people. So atomicity means, let's say that this is a piece of memory. I'm showing this on my video, right? And this processor on my right is trying to put a value in this piece of memory, okay? And the processor that contains this memory is also trying to access the value at the same time, okay? So so usually if this processor is not interfering, you get an exact value what is there in the memory for the destination processor. But what will happen when you are doing things asynchronously is that simultaneously the first processor or the right processor can write a value here, and at the same time the left processor can read the value from the same memory. And if the writing did not finish of all the 8 bytes or 16 bytes that you use in your computation, you will get junk values. Okay, so that means we want to do an atomic access of these integers or floating point numbers when we do these computations. I can go over this issue in more detail towards the end of the lecture. Okay, I think I need to speed up, right? Let me do that. So now typically if you take any parallel code, it uses NPI, I send, I receive. When you want multiple buffers, you can stack up the buffer like this. But this will fail, such a communication model would fail for asynchronous computing because you have to track the time level and you don't know whether the value has reached or not and so on. To do that, we have developed a new scheme which uses what is called a ring buffer. This is the buffer, additional buffer that we create. The S values are the values that we want to send from task 1 to task 0, or from the right processor to the left processor. B are the buffer points. So instead of sending directly the S values from the right to the B values of left, we first send them to the buffer. So here we send, we have 3 pipelines of messages that are going on. The nth value is in red. That means the communication is not yet finished. And in the other cases, they are in black, which means the communications of n minus 1th and n minus 2th time levels are done. So now to go ahead and compute the values at the left processor, we cannot have the nth value. So what we do is we take n minus 1th and n minus 2th values and go ahead and with compute things. So that means we are not waiting for this nth communication to finish. That means the processors can go ahead and compute and they are occupied. That means we are doing necessary useful computations while the communication is happening. So this is where we can get better scalability or better computation communication overlap. Okay, so there is a huge, I mean, there are several variants of this that we have developed based on one-sided and two-sided communication models. But let me go over the overall algorithm. So any PDE solver, we start with first some initialization. We run the first n loops to just populate this buffer in a synchronous fashion. So this is usually of the order of 10 time steps. And then we next march the next million time steps in the blue, using the blue code. where we do a lot of computation communication overlap, use the AT schemes, as well as do not. Okay, so with all of these things, I can again go over these details in Q&A. We will move to the performance results. So now, how do we quantify the performance? We will quantify the performance in two aspects. The first one is the distribution of delays. Okay, so what is the delay that you are actually measuring on a supercomputer? The second one is the strong scaling graph, and then the third one is weak scaling. We do this for simple 1D problem as well as a 3D turbulence problem. And we choose the parameters of the simulations that are close to what we would observe at next generation super exascale computer. Okay, so this is a probability density function that we obtain for the delays. So the delays are represented by the x-axis, which is k tilde. We give a maximum possible delay of 20 time levels. That means each processor can have a value of -20 to +20. So if you are at 0, the delay is 0. That means you are at the current time level. If you are having a positive value for k, which means you are getting a delayed value. If you are getting a negative value for k, that means you are running really slow and you are getting a value from the neighboring processor, which is from your future. Okay, so this is a negative delay. So what and different lines that you observe in this graph are measured for different processors that are used in the simulation. Here we have used 8 processors, so you will see 16 lines here. And what you see is that the peak, the mean of the simulation is around 10 time levels. So on an average, you expect 10 time level delay on this particular problem, on that particular machine that was run at Lawrence Berkeley National Lab. And the standard deviation for the delays is around 5 or 6 time levels. We have improved the MPI implementation, right? So now we have seen that the numerics also gets affected by the kind of MPI and hardware software that you use. So we did that exercise and you had a better MPI model, and we moved the PDF, which are centered around 10 time levels, to one that is centered around 0 time levels. So in this particular case, we observe a mean delay of 1 time level and the standard deviation is 2. So why these statistics are important, statistics of the delays are important, is because they also affect the accuracy of the solution, right? So we need to get these numbers to also define the accuracy of the simulation. So finally, I'll come to the graph on performance, right? So if you take any traditional way of computing things, eventually you will hit a point where your computations or the scalability is communication bound. So that means you will move away from the ideal scaling line, and this is a gap that is incurred due to the communication cost. Okay, so this is again similar to the strong scaling graph that I showed you in the early part of my talk. So when we do the same thing asynchronously, you see the blue points, these are parallel to the dashed line, we are able to maintain linear scalability. And I should tell you that this is a log graph. That means you are actually significantly increasing the amount of communication overhead when you do things asynchronously. Okay, so this was presented at SC and also in one of the other papers. Then we went, so this was done for a simple 1D problem. We went ahead and did this for a 3D Burgers equation problem, where we explicitly computed what is the computing time and communication time. So let me show you that in a bit more detail here. So here we have considered a simulation with 120 cube grid points, right, about 1 million grid points, and we have gone up to 12,000 processors on the Swiss supercomputer. What we observe at a low number of processor counts or node counts is that the communication time, the red line is much above the yellow line, which is the communication time. And if you sum up the two, you will get the total simulation time, which is the purple line. As you increase the number of processors, the computation time goes down. This is based on the linear scaling that we were expecting earlier. But what we see is that the communication time is nearly the same. Okay, and at one point, the communication time overwhelms the computation time. This is where the things start deviating from ideal scaling line. Okay, so we do the same thing asynchronously, and you see that as we increase the number of processors, the communication time is going down, and the communication time is also going down because we do not synchronize. And in this case, the yellow line has always been below the red line. So that means you are not communication bound anymore when you do things asynchronously on the right figure. The second thing that I want to show you from these graphs are these error graph, the error bars. We have performed these simulations 20 times. So each simulation configuration, we have done 20 simulations of those to accumulate what is the variability in the performance at different times on the supercomputer. So you see that the huge bars on the communication are experienced in the synchronous case. When you do the same thing asynchronously, this variability has also gone down. So the performance variability has come down. The mathematical asynchrony that we introduce at a finite difference level is able to absorb that amount of performance variability and reduce those effects when you do things asynchronously. That is also observed in the total time as well. So to look at finally the strong scaling graph, where you take a particular problem, in this particular case, the 120 cube problem, and increase the number of processors. The light and dark purple ones were done using the traditional synchronous algorithm. The red and the yellow ones are done using the weakly synchronous or the asynchronous algorithm. We have used two different communication models. The first one is NA, which is a one-sided communication model. The second one is NB, or non-blocking, which is a two-sided MPI I send I receive communication model. As you increase the number of nodes or the number of nodes to 1,000, which is equivalent to 12,000 processors on that supercomputer, we observe that the speed up is twice at the extreme scale. And now you imagine this is just with 1,000 nodes and with around 12,000 cores. The next exascale supercomputer will have million cores. So this graph would widen much further, and we would be able to scale better with this exascale machine, right? So we do the same thing in a weak scaling fashion. In the weak scaling case, you take a particular problem, computational effort per core, and as you increase the number of processors, you also increase the size of the problem, so that the overall effort should remain constant, or the execution time should remain constant. So ideally, we should find a flat line. If you do the things in the traditional synchronous fashion, which is a TS, the purple curves, you see that you are not maintaining a flat line, but it deviates from the flat line. And you do the same thing asynchronously, it remains nearly flat. And the speed up that you expect from the synchronous and asynchronous case is the 2x speed up. Okay, right. And as you move towards exascale, these numbers will become much bigger. That means you can expect faster and faster solutions with asynchronous computing. So with this, I finish the performance results. I will be discussing any questions on this towards the end of the talk. I will just take 5 more minutes to also explain the research highlights from our lab. We are working in addition to asynchronous computing and on a problem related to energy. So here in this slide, I show you the strategy towards green or the next generation energy and power supply. Okay, so what you do is you want to use renewables as much as possible, but you know that not every day is a sunny day and not every day is a windy day. So these sources of energy are very intermittent in nature. So what you do is when you have excess wind or excess sunlight, you take the additional power that you have generated to electrolyze or to produce hydrogen from water, right? So that will give us hydrogen fuel. We will also want to supplement on some of the high load days with some natural gas or fossil fuels. And then you also want to come up with biofuels or biogas that you get typically from molasses and all of those processes. So now a new next generation gas turbine should be able to burn all of these different fuels, which will have different chemical characteristics or different combustion characteristics in the same gas turbine, and substantiate that to get a stable power, right? So you want to get as much power as renewables. That may or may not be sufficient. So whenever it is insufficient, you want to run your gas turbine that can operate with different kinds of fuels and produce a stable power transmission. So this is the overall big picture. So to achieve a fuel flexible gas turbine combustion, one of the concepts is the reheat burner or a two-stage combustion concept from Ansaldo Energia. A schematic of their GT36 H class gas turbine is shown on the left. This has two combustors. The first one is the typical swirl stabilized or bluff body stabilized combustor. The second combustor that you see takes the air from the first combustor which is really hot, and stabilizes the flame typically using an auto ignition mode. And this stage is very important because this determines the overall efficiency of combustion as well as the engine operation. So what we have done is we have recently performed using the S3D code a direct numerical simulation of this second stage combustion. On the right, I show you a typical realization that we obtain from the DNS. The contour, the structures are of vorticity, right? And the coloring from blue to orangish red are the temperature contours. So you see that initially they are cold, and upon combustion happening in the combustion chamber here, you see the red color flame, and post flame the temperature rises to orangish color with a large amount of vorticity that is present. So this simulation was performed on 1.25 billion grid points on 50,000 processors. So the idea here was for us to understand the flame stabilization mechanism, the combustion characteristics, the flame structure, and so on. And one of my students, Akash, is currently working on doing this at much realistic pressure conditions that are relevant to the next generation hydrogen-based gas turbine combustors. The next problem is related to aerospace engine. So here the issue is with respect to the flame stabilization in scramjet engines. So this can be thought of like typically you take a candle, right? And you want to, you can easily light the candle with a matchstick. Now you turn on the fan, right? And now you try to light it. It becomes very difficult. So the issue there is that the air that surrounds this candle wick, right, blows off the flame. So similar is the issue where the flow is coming at Mach 2 inside the gas turbine inside the scramjet combustor, and you want to create a low velocity region to stabilize the flame. So we are currently focusing on cavity-based stabilization method and looking at this in scramjet applications. So this simulation was run on 2 billion grid points, and here the fuel is ethylene. In the earlier case, it was hydrogen. So here we have 10 times more PDEs that we need to solve, and the computational effort was performed on 200,000 processors on the Lawrence Berkeley machine. And we also, as I said, we generate lots and lots of data. So we want to use machine learning methods to identify extreme or anomalous events, which are really important to understand either in the gas turbine case or in more general cases like cyclones in weather or crack propagation in materials. So what we are looking at is a method to detect anomalies in scientific data. So a typical example that we could use is a principal component analysis. So let's say that we have two data sets. The first one is a data set which has two variables v1 and v2, and these are the samples that we get for the data either using measurements or through simulations. The second data set again has the main cloud of cluster of points, but in addition to that, these has these additional points that are away from the main cloud. These represent something like scientific anomalies, like a crack, signatures of a crack, or signatures of an combustion instability or an ignition process, and so on. So we can use typically a principal component analysis, obtain the eigenvalues and eigenvectors. So here I plot them. The first principal value is the solid line. It is oriented along the maximum spread or the variance in the data. The second one by construction is orthogonal to that. And these are the principal values. The second case where we have the data set with an anomaly, we do the same analysis and we find that there is hardly any change in orientation of the principal vector, nor a significant change in the values of the principal values. So the conclusion here is that if you go do traditional dimensionality reduction or use elliptic envelope kind of methods for anomaly detection, you will not be able to find the signature of these points in these analyses. So these second order moments mainly capture the variance in data, but what we are interested is in higher order moments and extreme events. So we went ahead and developed a method based on the fourth moment, which is the kurtosis. So the vectors that we get from kurtosis are given by these blue lines. The solid blue line, which is the first principal vector, now you see is oriented along the cluster, which is anomalous. We arbitrarily move the cluster to some other location. The red line still tries to capture the variance in the data. However, the blue line quickly reorients itself now to capture the new location of the anomaly. the same that is the one that you observe in the third graph also. So what we have done is we went ahead and developed an anomaly detection algorithm for scientific data based on this mathematical concept. And we are now currently working with one of my students, Shubham Kulkarni, on developing a framework that can be applied to any of the scientific data sets, and also comparing that with traditional methods like support vector machine, isolation forest, any of the clustering methods, and so on. So these are some of the highlights of research from my lab. So finally, I want to conclude my presentation. So here I have provided a brief overview on the basics of PDE solvers and parallel implementation. I have presented the concept of asynchronous computing method. I have shown the theoretical framework development, which gives us an expression on how error depends on not just on the numerical parameters, but also on the simulation parameters. I've shown you the scalability of codes, how asynchrony can improve the scalability, and I have shown you a path for exascale computing when for PD solvers. So currently, what we are working on is extending the simulations for 3D reacting flow solvers for DNS, and also coupling these with CS models like the asynchronous runtime models. One of them that we are working is with Stanford on the Legion region programming model. So with this, I would like to conclude the talk, and thank you all for listening. I'll be happy to take some questions.
Thank you, Dr. Aditya. And I really thank you on behalf of the Mechanics Lecture Series team. And it was really an interesting talk, at least for me. So we missed some questions in the question answer session. I'm sorry, Rahul, I didn't notice these questions before. So he is asking, the schemes can be developed for the other discretization frameworks as well, right?
Yes, correctly. So yes, they can be developed for other frameworks as well. And in fact, we are currently working on implementing that for discontinuous Galerkin methods. And we have promising preliminary results. So one of my PhD students, Shubham Goswami, is working on it.
Okay, so I have a follow-up question. Maybe it's quite related. So now with the approach that you have explained is based on either a spatial or a temporal stencil, right? And my question is here, like, how will it work? Or is there a way out? Or if you are thinking of extending this framework for other non-conventional meshing techniques, like let's say the image boundary method that you mentioned, or let's say the overset grids method where we have multiple meshes interacting with each other. So
so all of these things that are presented here are applicable for any sophistications on top of any finite difference or finite volume methods, right? So even if you take image boundary methods, you still have to exchange the data and so on. So what you have to do is you have to now come up with asynchronous interpolants, which we have done in the case of obtaining asynchronous Vino schemes, right? So those things can be developed, and you can perform asynchronous simulations, fully asynchronous simulations with image boundaries, embedded boundaries, or level sets, or any of those. In fact, one of our pipeline is also to extend this to Lagrangian framework, where you eject particles in an asynchronous fashion.
Yes, because these things gets more complicated when we have the multiphysics problem. So let's say we have fluids and structure, and they themselves are interacting, and a coupling algorithm works at the interface. So it's actually a bit difficult for me to imagine at what stage or what would be the point where we exchange data between different processors and how you apply this asynchronous method. So that would be really an interesting future work, maybe.
Yes.
So have you tried any coupled problem with this technique?
Yes. So coupled problem in the sense that so the example that I can give you that we have just submitted is reacting flows, right? Where we are coupling the flow equations with the chemistry equations. And these chemistry equations are rapidly changing, right? So the reaction rates are governed by these Arrhenius laws, which are exponential in nature. So if you introduce any asynchrony, which is linear in terms of velocity or temperature, in obtaining reaction rates, those things might get amplified because of this exponential function, right? May turn the solution really bad. So we have just submitted a paper that validates all of the asynchrony-tolerant schemes and shows that we can still manage to get accurate solution even with rapidly varying processes.
That's interesting. Yeah. So Rahul has another question. What
Yes.
profiling tools do you use for the code, and what language
Yes.
framework
Excuse me.
has been chosen? Yes.
Yes.
Hello.
Yes, Rahul.
Yeah. I mean, I
Yes,
have a
Rahul.
few follow-ups to the previous discussion, like before moving
Sure,
to the
please.
profiling tools. So I
Yes.
think, like, I mean, as you had mentioned, that these can be extended to other discretization frameworks as well, right? So
Yes.
I think the broader question would be to have a framework of
Yes.
analysis and development of these schemes for any discretization
Correct.
method, right? Be it finite volume or
Yes.
inverse boundary, any sort of scheme that we would want to come up with, we would need to
Yes.
have a way to go about the development and analysis of the asynchronous part.
Correct.
Where, like,
Yes.
as in, we need to know where to add the asynchronous part, and
Yes.
so which means that we would need to have some sort of diagnostics and metrics that we need to evaluate the scheme on,
Correct.
right?
Exactly.
So
I totally agree with you. So let me answer this for you. So
okay,
in the 2017 JCP paper, we have
okay,
laid out the framework on how to arrive at schemes, how to deal with the truncation error terms, and
okay,
that paper actually explains on how you can derive schemes for derivatives of arbitrary order to
okay,
arbitrary levels of accuracy.
okay,
And we show 2 or 3 methods to develop these methods, and we have used that 2017 paper, the framework that we laid out there in deriving 80 Vino schemes in the one we have just submitted.
okay,
Yeah.
okay,
So yeah,
and
your observation is correct, and we are trying to address that. Yes.
okay. And so one other key thing for multi-physics problem would be to select a benchmark problem, right? Like a benchmark
Mhm.
problem, as in
Yes.
without which we wouldn't be able to say that the scheme can be extended to a 2D or a 3D case. Like, for example, if
Correct.
it's a multi-physics problem, uh,
Mhm.
like we might have to start right away from a 2D problem, right? Be it a
Correct.
vibrating cylinder or even a vibrating string. It's still a 2D problem because you have another
Yes.
degree of freedom that you would have to work with. So in
Yes.
that case, I think even reacting flows or any other
Mhm.
system that we are considering for multi-physics, what do you think would be a good way to go about choosing such a benchmark problem?
Correct. So what we have done, I will tell you in the context of reacting flows, is that we did not directly implement all of this in a 3D code, and which would obviously take a lot of development time, and we do not know whether it will work or not. So there are high risks as well. So what we
Yeah.
have done is we have implemented this in a simple 1D code, right? 1D
Okay.
reacting flow. So overall,
Okay.
the kind of nature of chemistry that you would encounter, everything would remain the same, but the flow is 1D. So we
Okay.
have extensively developed benchmarks based on standard problems that are used to validate either premix flame, auto ignition, non-premix flame, detonation. So we have validated with all of these results. So
Okay.
the paper that is under review we have considered around 7 cases in
Mhm.
combustion of different types of nature of combustion events, and
Okay.
validated for all of them, both in terms of
Okay.
physical space as well as spectral space.
Okay. Okay. And
Yeah.
yeah, just a follow up to that. So, what do you think is like? I mean, I think you have this complete group set up for working on these things, right? Like, what do you think is a good way to go about starting on this area for, let's say, other domains? And how would you suggest we go about working in this
Uh,
area?
I
It's
mean,
a very vague
applying
question,
AC,
but
right, applying asynchrony to other set of equations or things, is it? Is that what you're
no,
asking?
I'm saying like the entire. Okay, I think whatever you have shown in your conclusions seem to be a very good
Ah,
roadmap as to how we go about um, understanding asynchrony and also develop asynchronous solvers, right?
yes.
So I think
Okay.
we can take this as a good roadmap for anyone, any domain as such. Like uh,
Yeah,
first,
I guess so. Thank you
yeah,
for that.
yeah. So I think I would certainly take this as a roadmap even in my work. So I mean I work on the same lines as Chandan does, but
Okay.
I have
Okay.
my focus is more on the lines of data-driven modeling and simulation of FSI systems. So
Sure.
I work on
Nice.
machine learning for science, so even including model order reduction, and I work on both
Okay.
forward and inverse problems. So that's kind
Okay.
of my
Okay.
focus area currently. So even if
Okay.
if I could, and basically working with legacy data currently, and we were able to we managed to accelerate our immerse boundary method solver using OpenACC and ported it to
Okay.
GPU, and we have tested it to an extent, and we are implementing that, like, the same strategy for all the other variants of our code. And
Okay.
I think it's currently in OpenACC, which means shared memory kind of a framework. So we want to move to
Correct.
MPI, CUDA, and other frameworks,
Yes.
and more data parallelism and reduce the communication overheads as well. So this
Sure.
this is like probably striking the right chord with what we might want to do moving on.
All right. Yeah. Thank you. I'll be happy
Thank
to
you.
work with you if you are interested.
Yeah, certainly.
Yeah. So something that we are also looking at the whole simulation workflow, as I mentioned in the first few slides, right?
Yeah.
To incorporate scalable solvers with proper data analysis, which are data driven, like what you are working on. So also build these reduced order models in situ, because you cannot store the entire data and the IO costs are really large. So can the models learn on the fly?
Online,
Right. So that is also what we are looking at. So we are looking at both in terms of programming models as well as the machine learning part.
Okay. Yeah, that's a very interesting field. I mean, in my opinion, as well, I find it really fascinating because you can come up with so many different combinations of methods, and however, a very rigorous standardization of such methods is what is required currently. Because with the plethora of models that are available, or model architectures that are available, or even programming models, as in getting to the right choice is becoming all the more difficult.
Yes, I totally agree.
So
things are becoming more complex as we increase the scale.
Okay, so I would like to ask the other participants. I want to thank all of you for joining this talk. Do you want to ask any other questions to Dr. Aditya? Please unmute yourself and go ahead.
So yeah, I see that there are several questions from Deepak on the chat, but if you can just please unmute yourself and ask, that would be great.
Yeah, please go ahead, Deepak. I'm not sure whether he's present currently,
so,
but he is, I think. I can ask you instead of
sure.
him. Yeah, so basically he's asking slide 10, how the equations will change in the case of a multiphysics problem that you already answered, I think.
Yes, yeah. I'm not an expert on those equations, right? But yeah, I mean, the nature of the treatment would remain the same.
Yes, and he also asks on slide 5, what are the options available for visualization of large amount of data?
Yes, so currently we are collaborating with people at UC Davis. So there is a scientific visualization group led by Professor Kwan Loma, where we are looking at, so these days you typically look at these Facebook stories or YouTube stories, right? These 1-minute videos that give you a small gist of. So now let's say that you perform a really large set of simulations for different parameters. So can I see the essence of the data, right, in a snapshot? So that is what we are looking at, and getting to that also is very difficult because now the data is available across 1,000 or 10,000 or 1 million processes, right? So we are looking at scalable visualization. I'm not an expert on it, but I do work with them, providing them all the necessary feedback from the physics point of view or computing point of view, and they take care of the visualization point. So they are also working on in situ methods for coming up with these stories of data stories, right? And also looking at how we can actually perform some on-the-fly analysis and visualization without storing the data to the disk.
Yeah, that's an important aspect. We all have to, mostly who are working on this higher order turbulent simulation, it's a big issue, I think. Yeah.
Yes.
So if the others do not have any question, I would like to ask 2 more questions. I mean, I'm very curious about. So first thing is, like, as you were mentioning, like you are going towards machine learning. So are you really targeting the, like, what type of techniques you are targeting to employ to find these anomalies? Are you actually going for the physics informed neural networks or not?
Okay. So let me answer this question in 2 points. The first point is more, if you see machine learning applied to fluid mechanics, most
Yes.
of this has been in the context of modeling, right?
Mm-hmm.
So in terms of developing turbulence models, and this is where the physics informed networks would come into place, where you want to train the model for either the coefficients in the stress equations or the subgrid stress values itself, right? With the physics component being the generalizability of the relations, or the constraints such as conservation of mass momentum being applied as loss functions and so on. Right. So I don't want to run that race of turbulence modeling. The
Yes,
way
that
I
was
see
my
myself,
question. Yeah.
right. So I don't want to run the race because there are several people more better experts than me who are already doing that. My interest is in the context of these large scale simulations, how machine learning can augment or accelerate these simulations in a better, in getting faster simulations and better data management,
On
right?
the fly,
So
as you were
there,
mentioning.
yeah, on the fly or post hoc also, right?
Okay.
Post hoc also, if you want to load the data onto these many processors and then run it, it is a bit difficult, right? So how do you reduce the data? And as I was mentioning in the earlier chat, so one of my collaborators is also looking at data compression methods, right?
Mm-hmm.
For these kind
Yes.
of large data sets. So I work mainly in the space of detecting these extreme events. This is important because that will tell us which kind of data do we store more rapidly at a much higher frequency. So you don't want to store the entire data. So for example, if you take this scramjet picture here, right, the
Yes.
flame is only in the bottom half, right,
Mm-hmm.
where significant reactions are rapidly developing and so on. So you don't want to do the data saves in the entire domain. So now the machine learning model, if it is generic enough, should be able to detect these subdomains to be the ones that contain the actual chemistry that is happening, or active chemistry happening. And it should trigger more data sets from these regions when compared to the entire domain. So this will result
True.
in
That's
a
true.
significant reduction in the amount of data that you would save to the disk, and also scale up your code.
Okay, that's true. But my question, another part of the
Mhm.
question was like when you are finding the anomalies, or you are basically
Right.
testing your algorithms, different type of
Mhm.
asynchronous algorithms,
Yes.
don't you want to verify with respect to the physics through
Correct.
maybe
Yes.
on the fly through neural networks or machine learning?
Yes. So yes. So to answer this question, I'll also bring up the point that Rahul has mentioned. So there are several options that are available, and you can use a combination of these, right?
Mm-hmm.
And come up with it. So you don't know what is best, and it takes some time to code up all of these things. So the first thing
Sure.
that we are doing in our lab is to develop a framework that will allow us to quickly plug and play different methods, right?
Mm-hmm.
Both in the serial setting, distributed setting, with in situ mode,
Yeah.
right? And then evaluate the performance of these based on the physics, where we define ground truths for some of the known data sets, and then come up with the tuning of the threshold or the weights and so on, right? And we use standard methods like the ROC curves, the confusion matrix, or the precision recall numbers to evaluate the accuracy of these methods. We not just evaluate the accuracy, we also look at the scalability of these machine learning methods,
Yeah, understood.
because we
Those are like two
yeah,
different aspects, actually.
yes, yes,
Yeah.
yes, yeah. So
Thank
something
you.
that might
So,
be really accurate,
yeah,
something that might be really accurate may not be scalable. Something which is
yeah,
scalable
that's
may
true.
not be accurate. So yeah, so we
We
would do
need
that
a combination.
evaluation. Correct, correct.
Yeah. So I have a last question, maybe. So have
Mhm.
you tried your techniques, your developed techniques of asynchronous computation on any open source solvers? Like I am very much into the open source solvers, open form. I really use it
Right.
extensively. And I
Mhm.
don't know if you are aware of that. Like they have recently secured a big fund for a project called Exaform, where
Okay.
basically they are implementing this exascale computing on open form, and they're basically
Okay.
testing it out. So I have done some basic course
Mhm.
project type of problem to check whether open form
Mhm.
solvers are really scalable or not in different supercomputers, including India's and Belgium's, the
Mhm.
supercomputers I use. And
Okay.
at some point, that's most of the solvers are really, I would say, at this stage is weakly scaled. So
Right.
yeah, probably there is a huge scope on work and maybe of
Mhm.
interest to you, and we can discuss
Yes,
in detail later.
definitely.
Yeah.
Yeah, sure. So my brief answer for that would be yes, these kind of methods can be put in place to into open form. But to do that, right, we need to have the right people who know the in and out
Yes,
of
yes,
open
exactly.
form.
We need a good collaboration. So, yeah, in that
Correct.
respect, probably we should have a separate discussion on this because I
Okay.
know the models or solvers that we are interested in this kind of problems,
Mm.
but we probably can implement your models into that and maybe
Mm.
look into the scale-up factor. Yeah, that could be a
Mm.
very good work.
Yes.
I mean, and good
Yes.
contribution. Actually, the open form community is also going towards that, and probably I
Mm.
will send you a link separately on the Exaform
Sure.
project they're
Sure.
actually
Please.
undertaking.
Yes. Yeah. So right now we have our workbench that we have developed, and one of my students is also developing. Vinod is developing that for GPUs, where we are
Okay.
also. So GPUs are they can do very efficient computing, but they are really lousy at data transfers, right?
Yes,
So
true,
what we
true.
are looking at is how to hide the high latency and leverage the high throughput of GPUs using this asynchronous framework is what we are doing. We just got a grant on the Summit supercomputer to perform the simulations. The student is
That's
currently
great.
compiling the code and doing the optimizations. So hopefully maybe in a month's time we'll have the scalability results on Summit.
Yeah, that's great. We're
Yeah.
looking forward to it. Okay. Anybody else have any questions present in the audience? If not, we maybe again we thank you, Dr. Aditya, for such an interesting
Thank you.
talk. I hope to have more offline discussions with you regarding this.
Sure, sure. Yeah,
And
so yeah, so all of the audience, I request that if you have any thoughts or anything, please send an email. If you want to talk, we can set up individual meetings and
sure,
talk on mutual interests, right? And again, I once again thank both Ajay and Chandan for hosting me and giving me this opportunity.
you're welcome. So I would request Ajay to close the session if he's available.
Thanks, Aditya. Thank you so much for joining.
Yeah,
Thanks.
thank
I would also thank all the participants who have taken their time to join us here today. And I hope they found it very interesting and they have more questions. I think they would be welcome. Aditya would be very happy to answer them, I think. And you can definitely
you.
contact him. I thoroughly enjoyed the lecture, but it's like 2 a.m. for me here, so I'll refrain my
Yeah, I can
questions a
understand.
little later.
Yeah,
But really, thank you for joining, and
yeah,
it was really
thank you.
nice. And yeah, let's keep in
Yeah,
touch. Okay.
yeah, my pleasure. Thank you. Thank you. Bye.
See you, everybody.
Thank you,
Bye.
Dr. Aditya.
Bye.
Bye.
Thank you. Thank you.